In Chapter 9, we are going to discuss testing associations between categorical variables. Now, if you recall, early on we talked about two different types of variables. We talked about categorical and we talked about continuous. And the categorical variables, remember, are variables that we cannot rank, and they are our nominal and our ordinal variables. And then remember, our continuous are our interval and our ratio variables. In Chapter 9 within the textbook, I'm really not happy with how the textbook presents the information. I think it's very complicated, and I think on the level that this class is supposed to be designed, that it's going to be an introduction to statistics. And so I decided to put together my own PowerPoint. So there's about 17, 18 PowerPoints. And how I've designed it is we're going to talk about how we look at categorical variables. And once again, I said that they cannot be ranked. Remember, they're going to be variables that are going to have responses such as male, female. If there's some sort of a questionnaire, that it's yes, no, black, white. It's just categories. So it's not something that we can go from high to low, or being able to put in almost in a slide, where it can slide from one association to another. So with categorical, it's pretty basic. Yes, no, black, white. There's no ranking involved in that. The reason behind using a contingency table is we are trying to identify the frequencies of how two variables are relating to each other. So a frequency table of two variables is presented simultaneously. They're called contingency tables. And once we process through a contingency table, that allows us to recognize whether or not there is an association between the two variables that we're studying. And if there is, then we can continue on with our chi-squared analysis. The contingency table identifies association between two categorical variables. They are constructed by listing all the levels of one variable as rows in a table and the levels of the other variable in columns, then finding the joint or cell frequency association for each cell. So we have a little chart that I have put together, and what we're going to be looking at are individuals that are HIV or AIDS positive and individuals that are not HIV or have AIDS, and their sexual preference. And looking at this, I just have a little breakdown of identifying basically codes that will identify males, females, sexual preferences both. And you can see the coding is 1, 2, 3, and individuals with AIDS, without AIDS, and how we code it. So just a little chart that I put together looking at each individual, and looking at just 9 individuals here. And this is what we would go through for all 30 of the individuals in the study. So individual 1, are they HIV positive? Remember, yes would be indicating a 1, and no would be indicating a 2. So this individual does not have HIV because it's indicated by a 2. Sexual preference, remember, 1 is male, 2 is female, and 3 is both. In this particular person, their sexual preference is males. So this individual does not have HIV, sexual preference males. The second individual we'd be looking at, do they have HIV? 1, meaning yes. And what's their sexual preference? We know that 3 means both. And individual 3, do they have HIV or do they have AIDS? 2 means no, sexual preference, females. Okay, and so you can kind of see how that goes down the line as far as coding the actual responses. And so what we're going to do is take this information and now we're going to put it into a contingency chart. And this is going to allow us then to process and be able to understand what the frequency is. We can also get an expected value from how we multiply these categories, these rows and columns out. The chi-squared test allows us to make estimations based on the sums of the rows and columns and then compares the numbers observed with the number expected. Okay, so that's where we come up with that. Remember I said we know something about one category, but we don't know something about the other, and we have to make that estimation. Well, that's how this works in chi-squared. The cell frequencies are then summed across both rows and columns. The sums are placed in the margins, the values of which are called marginal frequencies. The lower right-hand corner value contains the sum of either of the row or column frequencies, which both must be equal to the number. And in this case, remember our number is going to be 30. And once we move on a little bit here, you will be able to see what I'm talking about. And as I said earlier on, the rationale for a contingency table is we're going to test the hypothesis to decide whether or not there is an effect present. So whether we're going to accept or not accept the null hypothesis. The effects in a contingency table are defined as relationships between the row and column variables. So in this case, remember we're looking at the relationship between individuals with HIV and their sexual preference. So that's what we'll be looking at. Are the levels of the row variable differentially distributed over levels of the column variables? And all we're looking at here is distribution once again, and being able to identify that relationship between columns and rows, and if the distribution is equal. Significance in this chi-squared test or this hypothesis test means that interpretation of the cell frequencies is warranted. Non-significance means that any differences in cell frequencies could be explained by chance. And remember, if things happen by chance, we call that error. And usually it doesn't have anything to do with our actual study. So non-significance would be associated with basically just the chance that you came up with the results, the data that you have. The chi-squared test is used to determine whether there's a significant difference between the expected frequencies, so what we would expect, and the observed frequencies in one or more categories. Does the number of individuals or objects that fall in each category differ significantly from the number you would expect? Is this difference between the expected and observed due to sampling variation, or is it a real difference? Okay, so once again, we're going to be looking at an expected, what we would we don't know anything about this other variable, but we're going to basically have an estimation in what we would expect our results to be. And then if there is that difference, due to a sampling variation, or is there really a significant difference in what we're looking at? Because remember, that's what we're trying to find out, associations between, and if when we're looking for an association, we're also going to be looking for the difference. What would cause there not to be an association, basically. So looking at a little contingency table that I put together using chi-squared as a method to test the hypothesis, this is what we came up with the 30 males that we have solicited information from in our study. So on the one side, you're going to see the rows across, individuals with AIDS and individuals without AIDS. And then we're going to compare it to the individual's sexual preference. So in this case, we see that the individuals that do have AIDS, 4 of them, their sexual preference is males, 2 of them sexual preference females, and 3 of them sexual preference as both. And the individuals without AIDS, we see 3 have male sexual preference, 16 of those 30 have female sexual preference, and 2 have preference of both sexualities. So remember, we said with the contingency table, we have to equal 30. So if you go down the side and you total up the AIDS and without AIDS, you add that together, 21 and 9, you have 30, and you look at the males and females and both totaled up, it's going to be 30. So that's what our number is going to be. That's what we started with, so this is correct so far. The next step of computation of chi-squared is computation of the expected cell frequency for each cell. This is accomplished by multiplying the marginal frequencies for the row and the column, so that's row and column totals, of the desired cell, and then dividing by the number of observations. So the formula for computation can be represented as expected cell frequency is equal to row total times column total divided by the total number. And in this case, remember, we have a total number of 30. So you look again at this, how the contingency chart is set up, and in the next slide it'll be a little bit more evident as to what we're doing here. But in this situation, we did the row total, which was 9, times the column total, which is 7, and we divided it by the total number of 30 participants to get 2.1. So that is our expected cell frequency for males with AIDS. Okay, so that's how we identify the frequency. Identify the expected frequency. And this is just basically what I had said on the other slide, how to identify the expected cell frequency. Row total times column total divided by the number. So using the same procedure to compute all the expected cell frequencies results in a table similar to this. So we saw on the previous slide, 7 times 9 divided by our total number of 30 is going to give us 2.1. Then we would take 18 times 9 divided by our total number of 30 gives us 5.4. Then we would take 5 times 9 divided by 30 would give us 1.5. So, and so on. That's how we would continue on. Computing each, you would do that with 7 times 21 divided by 30. And so that's going to give us the frequencies that we're looking at. The next step is to subtract the expected cell frequency from the observed cell frequency in each cell. This value gives us the amount of deviation or error for each cell. Adding these to the preceding table results in the following. So remember, we had found in the last slide the frequency, okay? And if we look at this same table with our observed, and then we had identified the frequencies by what we are expecting, okay? So that is just looking in the first row column. There are 4 adults males that we had talked about, and the number that we came up with on our expected frequency is 2.1. And if we would subtract, which is just the little formula O minus E, observed minus expected, you would get 1.9. Okay, and that would be the same on our second row column. We had talked about there being 2 males. We had identified from multiplying our 18 times 2 and dividing by 3, we got the cell frequency, the expected cell frequency of 5.4, and we would have subtracted observed minus expected, and so on down the line. And so if we look at the observed and the expected, we see that they're equal on the sexual preference and males, females. Observed, expected, and how we're really going to make a difference. The expected rows and columns for both equaling 0, then what we're going to do at this point is we're going to compute the difference by squaring it. And so in the next slide, we'll see how the difference is going to be evident with squaring our numbers. Each of the squared differences is then divided by the expected cell frequency for each cell, resulting in the following table. So you can see we have observed and expected, and then we have observed minus the expected squared, and observed minus expected squared divided by the expected. And you will see in the next slide the numbers that we come up with. So putting our everything that we have defined in our contingency table, the chi-squared statistic is computed by summing the last row of each cell in the preceding table that we just looked at. The formula would be represented by, and this is what the formula would actually look like. The x squared is chi-squared observed, okay, is equal to. And the symbol that looks like a giant E means total. So that would be the total cells times the observed minus the expected squared divided by the expected. So if we would take all the numbers that were in the contingency table that we've been working with, we would total all those up and come up with 7.66. Now, what we want to do, what we're really looking at here is comparing the observed and the expected value. And based on what our final numbers are, it's going to give us the indication whether or not this comparison that we're doing between the two variables is worth continuing on and researching more. That's basically what the chi-squared and contingency tables do for us. So in this slide, I talk a little bit about the model of no effects. And the model of no effects is exactly what it sounds like. There's no effect. And remember, with chi-squared, we're testing the hypothesis. So when I identify this as the model of no effects, common sense would say we're looking at the end result of our data having no effect, which would mean that it's the null hypothesis. Okay, and the null hypothesis, remember, is no effect, no relationship between the variables that we're looking at. And if we end up rejecting it, then we're saying, yeah, that there is some sort of a relationship that we can continue on. It's worthy of continuing on and studying this, whatever phenomenon that we're looking at. The interpretation of the cell frequencies may be guided by the amount of cell that each cell contributes to the chi-squared statistics, as basically seen in our early on when we were identifying, trying to figure out the expected frequencies. So observed minus expected squared divided by the expected value. In general, the larger the difference between the observed and expected values, the greater the value is. So the greater that difference in between those two numbers is going to show that there is more meat to what we're looking at here, that it is worthy of probably continuing on. And that kind of almost makes sense to, when you kind of visualize that, it makes sense. Like if there's a greater difference between what's expected and what we're actually seeing, then there probably is some sort of an association there. And it's just not due to chance. So in the example that we have looked at already, the example data can be seen that the homosexual males had a greater incidence of AIDS. Hence, if you look back on our chart, the observed was 4, and what our expected value was 2.1. Then would be expected by chance alone, while heterosexuals had a lesser incidence, observed 2, expected 5.4. This evidence shows that there's a direct link there, and that we, if we were actually doing this study, we could go ahead and say, yeah, that there might be some sort of an association between the individuals that are homosexual with AIDS, because obviously there's more observed than what was expected, versus the heterosexuals that we only observed 2, but we expected more. So that difference between observation and expected plays a big part in whether or not we think that this could possibly be a worthwhile study. And this, once again, here's our chart again if we wanted to look at what we were just talking about with observed minus expected. If the value of the observed chi-squared statistic is less than the expected value, then the model of no effects cannot be rejected, and the table is said not to be significant. And that just is exactly what we said in the previous slide. So if we have our observed statistic is less than our expected value, then it only makes sense that the model, there's no association, there's no significance. And it said that, no effects were discovered. And basically, the values that we have acquired could have just been obtained by chance alone. So you kind of want to look at, to me, if you think about it, like if we've observed less individuals that we're studying, if we've observed less than what we've actually expected, then there's not going to be that relationship there. In summary, the chi-squared test of significance is useful as a tool to determine whether or not it's worth the researcher's effort to interpret the contingency table, which we've said all along. That's ideally what we're looking at doing a chi-squared. Do we want to continue on with the data that we have acquired? The significant result of this test means that the cells of the contingency table should be interpreted. Okay, so once again, significance showing that there's an association. If it shows there's an association, remember we reject the null hypothesis and accept the alternate. A non-significant test means that no effects were discovered, and chance could explain the observed differences in the cell. So non-significant, not showing anything, then that would be that we accept the null hypothesis. There is no relationship. There's no nothing that's really showing that it wouldn't be worthy continuing on to do a little bit more studying on this particular topic.